Okay, let's talk about homonuclear diatomic molecular orbital diagrams. We're going to start with the oxygen fluorine neon framework. And the reason why is because the separation in energy between the 2s and the 2p orbitals is actually quite vast. Enough that in terms of how similar the energy, the similarity is almost not even there. And that will basically mean that whatever is happening down here in the diagram is completely irrespective of what's happening up here in the diagram. Alright, so now here's what I want you to notice. On each side of the diagram, we're going to have the atomic orbitals of the two elements for which we're going to form the bonds. Alright, so we have element E on the left side, and then we have element E on the right side. I'm going to assume that this is p block element, so we have the p and s orbitals as being your main valence orbitals. Oh, and mind you, we're going to do this for homonuclear molecules, but this could also be amended to include heteroatomic diatomic molecules. Alright, so roughly speaking, this is the way I kind of go about it. Now, as I was telling you, the separation in Rydbergs is between 1 and 2.1, and that's actually quite a bit of energy difference. So we are sure that these interactions will not happen between the S and the P's. Alright, so what we will kind of use, and this is very rough by the way, okay, don't take this as an absolute, but as a rough guidance to allow you to make relatively good diagrams. Technically speaking, when we try to make a sigma bond, we're going to go either up or down by a quarter of a Rydberg, and we're making a pi bond, we're going to go up or down by about 0.12 Rydbergs, right? So about half the amount of the sigmas. And this is totally rough, by the way. Okay, so it's not super great, but the idea is that the separation from the S to the P's is about 1 or 2.1 Rydberg. So these types of changes are going to ensure that we never actually touch the molecular orbitals with one another. Alright, so this is how it's going to go. In terms of the sigma bonds, we are going to go up in energy by 0.25 Rydbergs, and we're also going to go down in energy by about 0.25 Rydbergs. The same thing goes here. We have head-on p orbital coming in together with a head-on p orbital. So we have a sigma orbital forming, which goes down by about 0.25 Rydbergs, and another one that goes up to by 0.25 Rydbergs. So altogether, the separation here could be at the very least 1 Rydberg, but we've only gone up by 0.5, gone down by 0.5, so we still have 0.5 Rydbergs worth of energy of free space between these two orbitals. So they're pretty well separated. Alright, now notice that for the p set we have p orbital up, p orbital up. If you bring them together, you're going to create a pi bond. And you have a p orbital going in and out, and another one that's also going in and out. Bring them together and you'll create another pi bond. And there's really no difference between the pz and the px orbitals in here, or actually py, excuse me. So they're both going to be of the same energy. And basically you're going to go and create the p orbitals with 0.5 Rydbergs down, 0.25 Rydbergs down and 0.12 Rydbergs up. So the separation between them will be roughly 0.25 Rydbergs. Alright, now in terms of the look of the orbitals, the orbital on the very bottom occurs when the two s orbitals are in phase with each other. The one that forms on top occurs when you form the interaction with them out of phase with one another. And so the bonding interaction at the bottom is a sigma interaction, whereas the one up here is a sigma star interaction. And likewise, look at the p orbitals. You have two head-on p orbitals in phase with each other, so that's a sigma interaction. And up here you have them with a out of phase interaction yielding a sigma star bond. For the pi bonds though, you basically have your donuts, right? So you have p orbital next to p orbital next to p orbital, and they are in phase with each other, right? Top parts are the same shading, bottom parts the same shading. But for the pi star, which is the upper portion, the shading is alternating, right? So you have one portion that's shaded, the next one is unshaded, shaded, unshaded, and so on and so forth. Those are the ones that are higher in energy. Those are your antibonds. Alright, so that's the diagram pretty much for it. And notice that you have sigma, sigma star, sigma, pi, pi star, sigma. And for the pi systems, you have two boxes in there, right? So one box, two boxes, whereas the sigmas, you only have one box. And the idea is that each one of these boxes is going to take up at most 2 electrons, much like an s orbital can only have 2 electrons. A sigma orbital can only have 2 electrons. Each of the lines for the pi's can only take up 2 electrons, so both of those lines that represent the pi set can take up 4 electrons altogether. Alright, and pretty much the diagrams for dioxygen, difluorine, and dineon will follow this approach. You have your sigma, sigma star, sigma pi, pi star, sigma. And the separation energy gets greater and greater when you go farther and farther out. Now the interesting thing is that if you actually put in the electrons, right? Oxygen by itself has 6 valence electrons. 2 are in the 2s, 4 are in the 2p. So if you have dioxygen, neutral dioxygen, you'll have 6 electrons on the left, 6 electrons on the right, and together they will give you 12 electrons. And you basically start by dumping them into the lower molecular orbital. And remember, you can only put 2 electrons at most. Once that happens, you have to move on to the next orbital that's higher in series. What you're not allowed to do, though, is to jump from the first one to the third one or the fourth one. You gotta go in order. Start from the one that's at the very bottom, add 2 electrons. If you have more electrons, you move on to the next one from bottom to top. So for dioxygen, if you plug in, or actually put in the 12 electrons, you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And notice that for the pi star set, I put the 2 electrons as being spin up because there's 2 boxes that are of equal energy. So you have to follow Hund's rule before you start, pairing them up. Alright, now for difluorine, we actually have 7 valence electrons for each fluorine, so there's 14 altogether. So we place 2, 4, 6, 8, 10, 12, and 14. So now the pi star set is completely filled up. And for neon, we have 10 electrons altogether for each neon, so you're going to have 20 for dineon. So we have 2, 4, 6, 8, 10, 12, 14 and 16. So I'm sorry, I said that wrong. You have 8 electrons, 8 valence electrons for each neon, so you have 16 only, and you end up with 16 all the way up until the sigma star orbital. So that's going to have some consequences for us, and the consequence is something we call the bond order. This tells you actually what kind of bond it is between these two elements. It could be a single bond, a double bond, triple bond. The bond order is going to tell you. And the way you do that is with a rather simple formula. You look at how many electrons are bonding and you add them all up together. You look at how many electrons are anti-bonding, you also add them up together, and then you subtract the anti-bonding electrons from the bonding and you divide the whole thing by 2. So looking at dioxygen, specifically, this particular orbital is in pink. The sigma, the second sigma, and the first pi, those are all those are all bonding interactions. So you have 2, 4, 6, 8 bonding electrons. And for the stars, you have 2 and another 2, so you have 4. So you have 8 minus 4, which is 4. 4 divided by 2 is 2. So this is telling you that the bond order of dioxygen is a double bond. And you might have said that, well, geez, we already knew that by drawing the Lewis structure. We didn't need to do all this just to come up with, the fact that there's a double bond between the two oxygens. However, the one thing that the Lewis structure doesn't tell you at all, doesn't even hint at it, or even pretend to be roughly in the ballpark about it, is the fact that when you look at the molecular orbital, you actually have unpaired electrons. And what that means is that dioxygen is actually paramagnetic. Anytime you have unpaired electrons, it doesn't matter how many you have. All you need is one unpaired electron. The whole system is paramagnetic. Otherwise, if everything is paired up, we call it diamagnetic. But this is telling you that oxygen is paramagnetic. And the characteristic of paramagnetic substances is that they get attracted by magnetic fields. And that's kind of the astonishing thing. Here you would have thought, based on the Lewis structure, that everything was paired up, but in fact it's not. And if you actually think of it in this manner, Not to say that you have to draw it this way, but if you think of dioxygen in this manner, you can actually make sense of the fact that when you take liquid oxygen and you try to pass it through a magnetic field, it actually gets stopped by the magnetic field itself because it's got actual magnetism associated with it. Another thing that's also pretty cool about this type of setup of molecular orbitals is that you could actually line up and perform 4-electron spectroscopy on molecules, and you can actually find out, get a spectrum for different energies that tell you how many electrons are coming out of it. So you could actually integrate all these areas and see that there is like 2 electrons here, 4 electrons there, 2 electrons here, and then 2 electrons further in. So you can actually get a full spectrum of dioxygen, which is actually pretty cool. All right, now for difluorine, we basically saw that we have 2, 4, 6, and 8 bonding electrons, but we have 2, 4, and 6 anti-bonding electrons. And 8 minus 6 is 2, 2 divided by 2 is 1. So the bond order between the two fluorines is a single bond, as we already knew. But all of the electrons are paired up, so this is known to be a diamagnetic molecule. And neon, this is the interesting thing. For neon, if we calculate the bond order, we find out that there is no bond order at all. It cancels out. And so what this is telling you is that there is no diatomic neon that's chemically stable. And no particular bond length is expected for it. So that's one of the things. Now, what I'll tell you the truth is that yes, some of these molecules have been found, but the bond lengths are ridiculously long, longer than the size of proteins. So it's kind of dubious and a little bit ridiculous to call it a bond. But all right, now to finish this up, let's take a look at lithium and nitrogen. For these molecules, the bond separation between the s and the p orbitals is actually kind of small. It's only between 0 to 0.5 Rydbergs. So when you start combining your sigma orbitals or your s orbitals to make sigma bonds and your p orbitals, which are head-on, to make sigma bonds, the sigma star of the s orbitals meets up with the sigma of the p orbitals, and because they're so close in energy and they have the same symmetry, they actually mix with one another. And they create a new subset of molecular orbitals where you have your p set of slightly higher energy and your sigma star set of slightly lower energy, and you create one that's even lower of energy and another one that's higher in energy. And what ends up happening is that the sigma orbital that was here underneath the pi gets bumped up in energy, so much so that it actually goes past the pi orbital. So in fact of having the traditional sigma, sigma star, sigma pi, pi star, sigma, now we have sigma, sigma star, pi, sigma, pi star, sigma for elements lithium through nitrogen. Okay, so now with that premise, looking at the elements from lithium up until nitrogen, yes, we have pi first and sigma later. You simply input the value of electrons. Now, dilithium, there's only one valence electron per lithium, so 2 electrons total. Beryllium has 2 valence electrons, so 4 total. Diboron has 6 electrons total. Dicarbon, 8 electrons, and the nitrogen, 10. If you start filling the electrons, you have 2 electrons here for the sigma bond, and that's a bonding interaction, so this is guaranteed to be an actual molecule. Diberyllium goes from sigma to sigma star, and that's where it stops. Diboron goes from sigma to sigma star, and then you have 2 electrons which are unpaired, so this is paramagnetic. Dicarbon goes from sigma to sigma star to pi, and dinitrogen goes all the way to the second sigma. So what that means is that the bond order is 1 for lithium. For beryllium, you actually have roughly 0 bond order. For diboron, you have roughly bond order of 1. For dicarbon, bond order of 3, and dinitrogen bond order of 3. Now I'm kind of highlighting the pink range right here for diberyllium, diboron, dicarbon, because technically speaking, this sigma star orbital is not completely a sigma star orbital. It got a little bit stabilized by the interaction with the original sigma p and p orbital interaction. So it's a little bit dubious as to how much bonding or non-bonding they are. Now diberyllium technically is not guaranteed to exist, but because there is a little bit of dubious definition as to whether this is a true anti-bonding orbital. We've actually seen it in the past. Okay, I'll probably stop the video right here because it's been long enough.